one of the things that makes ecosystem services so important in Maryland is that it is we've seen quite a bit of loss of our natural systems over the last 40 years or so. So that was a map of Maryland in 1973, and this is a map of Maryland in 2010. So you can see the red is expanded quite a bit. That's the impervious area. And percentage-wise, in 73, we're about 45% forest, 40% agriculture, and 10% impervious area. In 2010, that impervious area has more than doubled, and we've lost nearly 500,000 acres of agriculture and over 200,000 acres of forest. That trend has gotten better in the last 10 years or so. Maryland has passed some laws that require replacing lost forests, but we've still seen, basically that has pushed a lot of the land area change into agriculture. So you still have development, but most of it is occurring on agricultural land. Or you even have some agricultural lands being converted to forests because of our forest conservation law. So a little bit about ecosystem services and kind of their state within government. So as most of you that are attending the seminar know, on the federal side, the integration of ecosystem services into decision-making is strong, and a lot of that is due to the great work that the folks at NESP have done in creating their guidebook and other guidance. We have efforts within the EPA, USGS, the USDA, Office of Environmental Markets. NOAA has several ongoing markets. So at the federal side, we've seen a lot of progress in the last 10 or 15 years. But on the state side, there's been relatively little development, and a notable exception being Oregon with their Willamette partnership. They have some of the most developed ecosystem markets of anywhere in the world, probably. But for most of the state government, that's not really the case. So Maryland has shown an interest in ecosystem services for quite a while. There was a working group that was established in the late 2000s that essentially explored the possibility of ecosystem markets in the state and other aspects of ecosystem quantification. And one of the main outputs of that working group was that we needed a consistent framework to quantify and value ecosystem services. And so when I was hired on to the Department of Natural Resources, I was essentially charged with developing a tool that will allow ecosystem services to be integrated into decision-making in the state. And that grew out of work that I did at University of Maryland, quantifying ecosystem service benefits particularly from forests. But the method has evolved and changed over time. But the framework was put out in that work. So most of you that know that are listening, ecosystem services have been defined in a number of different ways. There's the broad definition of just benefits that people gain from the environment. There's been many different typologies. The most well-known, of course, is the Millennium Ecosystem Assessment, but anyone that's really worked with ecosystem services knows that typology has quite a bit of flaws and kind of problems with it. I really like a simple approach, and one that I think the NESP guidebook outlines pretty nicely, which is defining ecosystem services benefits gained by people from the environment that are not already being paid for in a market and are contributing to a marginal increase in human well-being. At least that's kind of the operational definition for this project. And then that's really analogous to final ecosystem services. And a note that I'd like to make is that when we're looking at non-market monetary valuation, it can really depend on the perspective from which you're doing the valuation and the intended application. And so from here, all of this work is presented from the perspective of the state of Maryland and the benefits to its people, and the applications are to guide decision-making within our state. So, how do we value ecosystem services? In many cases, we value ecosystem services, and particularly non-market ecosystem services, by looking at willingness to pay. And for non-market services, that can be difficult because, by definition, there's not an existing market for them. So we rely on other methods like hedonic pricing, travel cost analysis, contingent valuation, et cetera. There are some emerging methods for valuation that take a different perspective, and instead of looking at individual willingness to pay, try and assess a societal or social willingness to pay. An example being deliberative monetary valuation. And I think that can make a lot of sense, looking at, particularly because we as individuals really don't have the proper context value ecosystem services. And I'll explain that more in a second. And there are a number of studies that focus on a biophysical value for ecosystem services. But the problem with that is it can be, and that can be a really useful way to look at it. But when you're translating that to value, oftentimes you can run into the problem of valuing an ecosystem function rather than an ecosystem service. So the service is really that benefit that's being provided for people, not just what's going on in the environment. But all of these options oftentimes miss this connection between the sustainability of the resource and the benefit that it's making to human well-being. And I can't say that the method I'm going to present here completely solves that problem, but I think it is a step in the right direction. So a definition of benefit-relevant indicators. They're measurable indicators that capture the connection of ecosystem contribution to people, whether there's demand for the service, and how much it's used or use value or enjoyed. So that's out of the NESP guidebook. And we're going to use benefit-relevant indicators and biophysical value interchangeably in this presentation. So quantifying how people are benefiting from a BRI can be difficult, particularly at the landscape scale. It can be hard to really nail down those benefit flows. So we're suggesting that a solution would be to look at the many ways that people are benefiting from an ecosystem service and taking an average for how you're benefiting, particularly looking at a marginal change in the benefit-relevant indicator. And this methodology has been laid out in a publication from last year in Ecosystem Services. So if you're really interested, please, I'd encourage you to look that one up. So we are using this method for ecosystem services where we don't have a certain value. So there's a few that we're relying on existing methods, and we have a pretty good idea of how they're doing that value, but we're using this for the ecosystem services that are less certain. This allows us to incorporate a range of value, and it allows us to look at value from the perspective of the state of Maryland. So it acknowledges that we're paying for the services in many different ways, and it acknowledges that when you look at where people view the responsibility of paying for ecosystem services or paying to protect the environment, they see it as a collective responsibility. It's bared out in many different surveys, and there's evidence for it within our rule of law. The public trust doctrine essentially lays out that the government is responsible for protecting our natural resources, and there's a really nice paper a few years back by J.B. Rule and Salzman in 2006 that explored exactly how that public trust doctrine applies to ecosystem services. So we look at a number of different ways that we're paying for these benefits, so that in some cases that isn't a market, or at least a market that's been created through regulation, like a carbon market. Through looking at replacement costs, the cost of restoring a natural system to then gain ecosystem services, through different mitigation fees, and then the cost of implementing regulations. So we're trying to look at a collective, in a collective way, we're looking at how people are paying for either increasing ecosystem services or avoiding loss of ecosystem services. So we're suggesting that this is, looking at these together, is a social value. Obviously, we're not looking at willingness to pay, so it's not a market value, but it's social value that's useful for decision making, particularly at the state level from a government perspective. So acknowledging that it's not the same as market value. So, and we're taking these and we're applying it to across the state of Maryland in a spatial map. So we know that ecosystem services vary spatially, and they vary spatially both in the biophysical quantity or benefit relevant indicator, and then they also vary spatially in the demand for the service. So to do a good job of mapping ecosystem services, you have to quantify both, and we're gonna outline how we've done that.
All right, so switching voices up here, I'm going to walk us through the set of services that we've mapped across the state of Maryland. There's 7 of them that we've mapped so far. We have air pollution removal, net carbon sequestration, groundwater recharge, surface water protection, flood prevention and stormwater mitigation, nitrogen removal, and wildlife habitat and biodiversity. For each of these services, we've mapped them across the entire state of Maryland at a 30-meter resolution, so a 30-meter pixel size raster data set. And we've leveraged, in most cases, existing ecological models that have either been created at the state level or the federal level, and then kind of tailored those to the purposes of the state. So as a kind of jumping off point, there's 2 major inputs that you'll see kind of permeating through all of the different models, and that is the area or extent of tree canopy across the state, which I have shown here. This layer in itself is pretty innovative. It originally was a 1-meter pixel size mapping of tree canopy across the state. This was created using a combination of LiDAR data and NAIP aerial imagery. And it was created originally for the NASA Carbon Monitoring System project aiming to map above ground biomass or carbon storage across Maryland, and in partnership with Jarlath O'Neill Dunn at University of Vermont. Now it's available for use for others throughout the state, so we've leveraged that information here. And what you see here is actually that information aggregated to a 30-meter pixel size. So for every 30-meter area, we know the meter squared of tree canopy in that area, ranging from 0 to 900 meters, being a fully forested pixel. The second major input is wetland extent. So I have here shown our kind of current leading wetland extent map. It's a combination of DNR mapped wetlands and NWI, the National Wetland Inventory. And I have those wetland areas just broken out by estuarian and palustrian, so freshwater and saline wetlands shown here. And so for the majority of our models, we've leveraged the kind of coefficients or the rates of different ecological processes and then apply them to the area of forest and wetland across the state. So our first ecosystem service that we looked at was air pollution. To acquire rates of air pollution removal by forests, and so I guess I should note that for this service we focus solely on forest services. So we, at this point, don't have the complementary values for wetland areas. So we looked to an online tool called the iTree Landscape Tool, which is created and hosted by the U.S. Forest Service. And this tool actually allows for calculation of uptake of 6 different atmospheric pollutants. So we were able to look at carbon monoxide, nitrogen dioxide, sulfur dioxide, ozone, and then particulate matter 10 microns and particulate matter 2.5 microns. And so what the iTree landscape essentially does is they use the National Land Cover Database 30-meter forest cover as their forest input, combined with population density from the U.S. Census Bureau at the block group level, as well as information on air pollutant concentrations and human health impacts of air pollution from the EPA. So they put all this information together to produce rates of air pollutant removal for each pollutant at the block group level. What I did is I went in and I kind of backed out the removal rates per meter squared of tree canopy for each of the block groups in Maryland, and then applied those air pollution removal rates to the updated tree canopy extents that we got from that 1 meter tree canopy mapping. So we had a more accurate picture of how many trees or how much tree canopy there was, and then applied those rates from the iTree tool. The amount of pollution that's removed varies geographically, and it varies based on the percent tree cover in the area, as well as the concentration of pollutants in that particular area. And so you'll see when we look at the mapping of this service that urban areas have a greater effect or a greater removal of pollutants because there's more pollutants there. I'm going to switch over really quickly to look at what that air pollution looks like. So we're going to talk in more detail about this Greenprint tool in the later part of the presentation, but wanted to use it for visualization. So here I have each of those air pollutants shown at that 30-meter resolution mapping. So you have the biophysical value of that, so the kilograms per year that are removed in each of those 30-meter pixel areas, as well as the economic value of the removal of that pollutant, so dollars per year. So an interesting thing you can see, the first 2 layers here are carbon monoxide. So right now we can see carbon monoxide removal across the state. Then if I switch to the economic value, you can see that spatial pattern changes, and you start to see that the higher value of the air pollution removal is running along that corridor between kind of Washington, D.C. and Baltimore, where we would expect that there is a much higher density of population. And so you can just see kind of the different distribution of, now this is nitrogen dioxide, ozone. So you start to see based on just what industries exist in different places in Maryland. So there's a lot of coal mining and some different industries up here on Cumberland that highlight it for some of the pollutants. Yep. And so we'll come back to this map here a little later.
Just to note, this is the same information that you could get from iTree Landscape, except that we have put the values on a per area of canopy.
Yep. Yep. So just applied it to a different forest extent. Yep.
Whereas they display it on the block group level.
And I do have, for each of the services, there's links that would take you to the websites where you could go and learn more about the models that we leveraged for each of those services.
So this just displays the value for each one of those air pollutants summed for the state of Maryland. So it's dollars per year for each one of those. So just to highlight that there's quite a large discrepancy between the value for nitrogen dioxide, sulfur dioxide, and carbon monoxide compared to ozone and then the 2 forms of particulate matter. Those are the ones that the model, the BENMAP model that the EPA produced, kind of shows that have the largest impact to human health.
Sorry, this is Lydia. Can you clarify where the dollar values come from?
So they were generated by the US EPA's BENMAP model. And those are displayed on the iTree landscape website. So these are the same values that you would get from the Forest Service.
Thank you.
No problem.
All right, so the next service that we looked at was carbon sequestration. We did look at both forest and wetland areas for the carbon sequestration service and used two different methods to map those, map sequestration in those areas. So I first built a model of forest carbon sequestration at the 30-meter scale. We again looked to the U.S. Forest Service iTree landscape tool, which gives rates of carbon sequestration at the block group level. So I again backed out the coefficients for carbon sequestration at the block group and then applied that to the meter squared of canopy from our high-resolution tree canopy map. The rate and amount of carbon sequestration varies across the state of Maryland. The primary sources of variation are tree age or forest age, as well as tree species composition. So in terms of age, we see that sequestration increases exponentially in the early years of a forest, like that first 30 years. And then as the forest begins to age and becomes older, that growth or that sequestration will begin to slow and then taper off and plateau at a certain rate when that forest reaches maturity. And then in terms of species composition, we find that deciduous trees such as oaks and hickories sequester more carbon than do evergreen trees such as pines or hemlocks due to a higher wood density trees. And from iTree, we found sequestration rates across the state ranging from 0.4 megatons per hectare For wetlands, then, this was one case where we didn't have a good existing model for wetland sequestration across the state, and so I kind of pioneered off in trying to develop something new that we could apply. And so we were trying to actually look at net carbon sequestration because, as many probably know, while wetlands sequester a large amount of carbon, they're also potentially large methane emitters. Methane being a much more potent greenhouse gas than carbon dioxide is. So we wanted to try to really capture that full greenhouse gas flux as best as we could. In terms of how those rates vary across space, both carbon sequestration and methane emission do vary across a gradient of salinity. Carbon sequestration decreases relatively slowly as you move from fresh water to more saline waters. And then methane actually decreases more drastically. So there's more methane emissions in freshwater wetlands, and then as you get into higher levels of salinity, that methane emission starts to drop off. So we find that as we get into the more saline waters, we reach a point where the methane emissions kind of fallen below the carbon sequestration, and so we start to see positive carbon sequestration benefits in those areas. And so to figure out actual rates that we could apply to our wetland areas, I dredged through a lot of scientific literature to identify published field sites where there was adequate data to calculate rates of both methane emission and carbon sequestration, so like soil accretion and carbon densities, and specific to the Chesapeake Bay region. So all of the sites I used were within the Chesapeake Bay as opposed to national or international studies. So together I had 121 sites for carbon sequestration and 34 sites for methane emissions, respectively. And I apologize, the next bullet here is a replication from the previous slide. So that is reflective of the forest carbon measurements. For both forest and wetland carbon, we use the social cost of carbon to price, or to value carbon, of $143 per megaton sequestered. And then I just have the two tables showing how those rates were calculated. So I broke it down by, for wetlands by type, so estuarian, palustrian, within estuarian, fresh, oligohaline, and mesohaline are the salinity variations, and then palustrian, I have rates for emergent and forested. And then also similarly, how the rates were broken down for methane emissions, so by salinity class. And we took the methane emissions and converted those to first carbon dioxide equivalents and then carbon equivalents to be able to kind of compare and do arithmetic with the carbon and the methane together. And then this is just a mapping of the net carbon sequestration for both forests and wetlands. So anywhere that you see as red happens to be an area where the models were showing carbon loss. And then ranging from the kind of yellow-green up to the dark green is increasing amounts of carbon sequestration for those areas. It was a kind of interesting phenomenon that we noted across multiple models. So we looked at different carbon sequestration models before settling with the I-tree model for forests, and there was this kind of persistent pattern of carbon loss in Garrett County, which after looking at it and talking to different folks, we've determined is because of the tree age in the area. So you have a lot of old growth, mature stands in that area, so you've kind of reached that plateau of carbon sequestration. And then similarly, you can see a pattern of a lot of carbon loss in what would be more freshwater or less saline wetlands, and then as you get down into the more saline wetlands, you start to see that switch to carbon sequestration as it starts coloring. The next service is groundwater recharge. Was fairly straightforward. I found a mapping of groundwater recharge through the USGS. So it was the estimated mean annual natural groundwater recharge for 2002. This layer was actually created for use with the Sparrow model, the spatially referenced regression on watershed attributes, which we used for another one of our services. I modified this layer to produce estimates of groundwater recharge in meters cubed per 30 meter pixel. It's important to note that while we looked at groundwater recharge in relation to forest and wetland areas, the largest driving factor for variation in groundwater recharge is really the underlying geology. So when we look at the biophysical, the kind of estimated potential groundwater recharge across Maryland, what you're really seeing is those more large-scale gradients in geology and soil types and things of that nature, rather than being driven by local-scale tree cover.
Right, so this is how we arrived upon a price per volume of groundwater recharge. So we looked at a few different ways that we're paying for water in Maryland. So simplest way is we're paying for water, our water supply domestically. We have a price for that, the market price. We're investing, we looked at a couple examples of investment in watershed protection. We tried to get as many examples from the state of Maryland. So we have one example from the state of Maryland, but we also looked at the classic New York City investment in their watershed and the amount they invested and the quantity of water that they stand to gain for that investment. And we looked at a non-market analysis for the value of additional water for recreation. So we averaged those three instances and got a price for the amount of water. So for all these, I should say, I'm looking at there are additional estimates of the price within the exchange classification, but then within, for the end value, we averaged the categories of exchange classification to get that end value. So there's multiple measures of the investment in watershed protection, but those were averaged together to get the measure of how the people of Maryland value that watershed protection. So for surface water, about half the water that we use in Maryland is from surface reservoirs. And it's pretty well understood that natural lands reduce the cost to treat water from reservoirs to the water quality standards for our use. And there are 5 major reservoirs in Maryland: Loch Raven, Liberty, Pretty Boy, Tridelphi, and Rocky Gorge. And those, the main users of our reservoirs are within that Baltimore-Washington corridor. So if we go to the next slide, we can see where those watersheds for the reservoirs lie within the state, mostly the kind of north-central portion of the state. And again, those are feeding the city of Baltimore as well as its suburbs. So go to the next slide. We can see how we valued it. We looked at measurement of the reduction in water treatment costs associated with a certain percentage of forest. We looked at the provision, again, that market price for water in Maryland. We looked at a study that analyzed the cost avoided of having a forested watershed in terms of avoided costs for upgrading a treatment facility, and then averaged that together. And so to get the actual ending value, we looked at the quantity of water that is being supplied by those reservoirs, and then the avoided, essentially the ecosystem service benefit of that quantity of water, and applied it kind of uniformly across those watersheds that are providing the protection. And I know that wasn't super easy to follow, but we do have a report that we will be posting on our website that you can kind of dive down into the nitty-gritty of this as well.
Okay, so the next service we looked at was flood prevention and stormwater mitigation. So in this case, we created an index layer that ranked areas based on the volume of water that was treated in each 30-meter pixel. To do this, we used a modified version of the Watershed Resource Registry stormwater preservation model. So this is a model kind of started in Maryland. There's a Watershed Resources Registry website. They have a suite of 8 different models looking at restoration and preservation rankings for different purposes of interest across the state. So we leveraged their stormwater preservation model, which ranks the relative capacity and stormwater load of areas across the landscape from 1 to 5. We modified their ranking algorithm to remove some of their specific targeting classifications. So, heavily weighting things like targeted ecological areas or stronghold watersheds. We wanted to look kind of across an even playing field. And then we also added a variable for slope to consider the slope in our model. We then estimated the range of stormwater volumes that were treated in each of those areas using information from the Maryland Stormwater Design Manual and the Virginia Stormwater Management Handbook. And in general, the spatial trends that you'll see are that riparian areas, forests, and wetlands, and watersheds with high impervious areas that have high impervious areas upstream receive large amounts of stormwater runoff as compared to more natural areas. So they're exhibiting a higher benefit in terms of treating those waters. And then things like soil type, presence of a floodplain, whether you're in a riparian area, et cetera, all also contribute to how much water is going to be absorbed and treated in any given area. So then this is just a mapping of that index across the state of Maryland.
So similarly to the other quantifications of the eco price of water, we approached stormwater by looking at different categories. So primary ones being cost savings, a tax that Maryland has instituted, and then the replacement cost. So we looked at the benefits that having forests and wetlands in your watershed can confer in terms of reduced cost of flood insurance. We looked at this tax that Maryland has instituted, the stormwater remediation fee, and then we looked at the replacement cost of the function of a forest or wetland with man-made infrastructure. Then averaged them together, and we got about 33 cents per meter cubed of stormwater runoff avoided.
Great. Next, we looked at nitrogen removal, which is a pretty big and important service here in the Chesapeake Bay region, because we do have a lot of agriculture, and the quality of our Chesapeake Bay water is really important to a lot of different actors. So to get at nitrogen removal, we leverage the USGS Sparrow model, so the spatially referenced regression on watershed attributes model. And this model simulates the loading of nitrogen and phosphorus across the Chesapeake Bay watershed based on variables such as land use, incoming nutrients from other watersheds, as well as atmospheric deposition of nitrogen and phosphorus. And so we took their information that was aggregated to the watershed catchment level and classified catchments in Maryland as having low, medium, or high nitrogen loading rates. We then calculated nitrogen uptake rates using average rates for low, medium, and high loading rate areas and different land cover types based on published scientific literature. So in palustrine wetlands, in general, we found that floodplains can process and store higher quantities of nitrogen than smaller isolated wetland areas. Pretty straightforward. And then in estuarine wetlands, we found that salinity seems to be a significant factor in the ability to process and store nitrogen, with more saline wetlands having more efficient nitrogen removal possibilities. So the table shows a breakdown of those different areas, so forest, floodplain wetlands, depressional wetlands, and estuarine wetlands. And then for low, medium, and high nitrogen loading for that particular land cover type, what the removal rate of nitrogen would be. And so this is the mapping of the removal rates across the state of Maryland based on that methodology.
So we priced nitrogen in Maryland by looking at a regulation that the state has where we will cost share for certain best management practices. We looked at the price of nitrogen in the Chesapeake Bay watershed in a market, and then we looked at the replacement cost for nutrient management BMPs. It's what it costs to implement a best management practices, and then we reduce nitrogen. And within that category, we looked at probably 20 different BMPs, but again, averaged that BMP cost and included it as that replacement cost. So the average for nutrients ends up being about $18 per kilogram of nitrogen, which equates to about $8 per pound of nitrogen.
Great. And finally, we have our wildlife habitat and biodiversity service. So for this service, we again created an index rather than a quantification per 30-meter pixel. So we looked at two input data layers in particular. The first was the Maryland Green Infrastructure Model, which was created by the Maryland Department of Natural Resources. And it looks at the size of habitat areas as well as the connectivity between those habitat areas. And so we assigned quintiles to this data based upon scoring of these green infrastructure areas from 1 to 5. We then considered, the second layer was the Maryland BioNet model, again produced by the Maryland Department of Natural Resources. And this model looks at the presence of either rare species occurrence or rare species habitat, and ranks these areas, again, on a 1 to 5 ranking. And so for the BioNet, we took the top 2 ranks of BioNet, the first and second quintiles, and considered those in our wildlife biodiversity benefits as well. And then for forests and wetlands that were outside of both the green infrastructure or the BioNet mapping, we gave them the lowest index value for wildlife habitat and biodiversity. So then this is just a mapping of that biophysical index. And this index has then been scaled from 1 to 100, with the 80 to 100 being the highest potential for wildlife habitat and biodiversity.
This ecosystem service was probably the most difficult to value, and particularly when considering that we're trying not to include any double counting. Do you think, I mean, habitat and wildlife habitat is kind of a fundamental condition to have all the other ecosystem services. But what we tried to do is isolate instances of payment that are targeted for either preserving or creating wildlife habitat. So we looked at Wetlands Reserve Program and a cost for investment there, spending by Ducks Unlimited, Conservation Fund, Habitat Banking, and all those they're looking at creating, they're really the spending, while you're getting all the other services with that spending, their spending is targeted for wildlife. And then we looked at, you can't just look at that and say, that's the yearly benefit because that's a one-time cost. So to try and take the one-time cost and translate it to a yearly benefit, we looked at how someone could write off a contribution over the maximum allowable time, which is 15 years, and consider that to be the annual benefit. So we considered both the average and then the high estimate. So the high estimate we considered to be the maximum value. So those 80 to 100, that's the value per acre per year for the 80 through 100 category, and then just linearly decreased it going down for the other categories. So there's obviously some assumptions made here, but we know this is an extremely important service and is also very valuable and drives a lot of spending in the state. So here is the map of when you add all the services up, where the highest value is. So the darkest blue, the highest values, and those tended to be wetlands, particularly some of the coastal wetlands, and larger wetlands that are in larger blocks of forest. So those got the highest value for wildlife as well as significant values for stormwater and other services. So if we add them all together, they equal $8 billion of ecosystem benefits per year. So quite significant. If you look at the entire agricultural economic activity in Maryland, it's about $9 billion. So again, breaking those services down by the different categories, units are in dollars per year. So going from the largest, smallest, and then the bottom category of stormwater is the largest at $3.1 billion per year, then wildlife habitat at $2.6 billion, groundwater at 1.2, nitrogen removal at $400 million, surface water protection at almost 250 million, carbon at 240 million, and then air pollution at 159. So all these services are providing significant value to the state of Maryland. And here's those same numbers, but just broken out in a bar graph instead of a pie chart. Maybe some people, can visualize things differently. And then to break it down into land use types, ecosystem types, we looked at the average. This is dollars per acre per year for forests. They're about $1,500 per acre per year. Coastal wetlands were the highest at $2,600 of the ecosystem types. And then freshwater wetlands were kind of in between at almost $2,300. And then we wanted to look at, is there a difference in the lands that we already have protected versus just the average for other lands? And we did find that, there's obviously some kind of autocorrelation going on in that we're protecting lands that part of the reason they have value is because they're protected in their larger blocks. Yeah. But it's still a somewhat interesting comparison. And then to break down the percent contribution to the total, so forests contributed 73%, freshwater wetlands 20%, and then coastal wetlands 7%. And kind of the take home from this is that while wetlands are about, when you look at it on an aerial basis, 20% of the area, but contribute 27% of the ecosystem service value, as you would expect looking at those per acre values. And then when we break it down by county, we're going to demonstrate the tool in a second here, if we have any time. Actually, I'm just going to skip this one. It just shows you what counties have the highest value. So one of the really neat things about this is it's not just information that's being created for research's sake. We have some actual applications that are both planned and in action. So we're working with the department's land acquisition and planning group to integrate this information into their decision making, and they control the money they invest is around $100 million per year for land acquisition and planning, that includes the state and local spending. We're working with our restoration group to integrate this information into how they select projects for restoration. So basically looking at the ecosystem service benefits of restoration. And we've worked with our Maryland Park Service to evaluate impacts to a park. In the case that we've done so far, we looked at a natural gas pipeline that went out of their existing easement and disturbed some forest and generated a value using this method. It was a net present value of the ecosystem service benefits that was actually accepted by the natural gas company as compensatory value. The future work, you may have noticed that we didn't talk about the Chesapeake Bay. That's obviously extremely important in Maryland. We want to be able to include a spatial analysis of those benefits. We want to look at agriculture. This is not going to be a static map. We're going to update this over time, hopefully on a 2-year basis. And then we're collaborating with partners. We have partners of in-state with different agencies and nonprofits and universities. Interstate, we're working with Pennsylvania, and federal partners. We work with the Chesapeake Bay program, as well as